So again, my name is Matt LeMay, and today's presentation is an introduction on generative design for Inventor users. A little bit about myself to get started. Again, my name is Matt LeMay. I've been at Autodesk now for 4 years. I'm located in the Boston, Massachusetts office. And my prior experience is with additive manufacturing for the medical industry and aerospace composites. So the agenda for today, and I know we're running a little bit late, so once again, I do apologize for that, but I hope we can still have a very productive webinar today. The first and the most important thing that we hope to provide to you today is an introduction to how generative technology can provide value really to every industry. So we call this the why. Second, we'd like to help you with an introductory knowledge to generative design, so how to get started, and what some of the considerations that you might have to be on your own projects. And then finally, we'd like to help you learn how to get additional training and support. So to get started today, before we jump into some of the content, I'd like to launch our first poll question, just so we can get an idea of the experience throughout all of the attendees that we have. So the question should be appearing on the screen now, and is, what is your current level of experience with generative design? So we'll leave this open for just a few more seconds. And thank you for everyone that answered. It looks like the majority of people are pretty new to generative design. I should be sharing that poll now. So this is pretty much par for the course. Generative design is a fairly new technology. That's why we're holding sessions like this to really help you get up to speed. So thank you for everyone that's joining us, and thank you for everyone that answered that poll question. So first, to get started, we'd like to talk a little bit about where Autodesk sees generative moving within the industry and why we think it's so important. So as we look at the history of CAD technology, the first major transformation was the shift from drafting boards to 2D CAD. So as we did that, the engineer was now able to work on their projects electronically, massively increasing the value that they were able to provide. The next major shift happened with 3D CAD. So again, we took that transformational leap that drafting boards had to 2D CAD, and we did the same thing with 2D CAD to 3D CAD. From here, the next major shift was finite element analysis. With finite element analysis now, before actually producing the product itself, we were able to analyze and simulate and validate that that product would actually be viable for what it needs to see in real life. And then finally, we have generative design. So with generative design, we can now lead with our objectives. We can provide a range of manufacturing types and a range of materials and explore hundreds or thousands of higher performing options that are meeting all of the structural requirements and also, again, those manufacturing requirements that we set. So when we look at the generative process today that we're really trying to affect, when we talk to our customers, they've always told us that when bringing a product to market, they'll start with a small handful of concepts, maybe 4 or 5. They'll then evaluate those for structure, for manufacturability, and in the end, they're bringing a product to market that, while it may have taken them longer than what they would have liked, it's also significantly similar to every other product they brought to market because they're not exploring a wider range of concepts at the front end. So what we're really trying to affect within generative design is at the front end of that product cycle, we're leading off again with our objectives, and we're solving for hundreds or thousands of higher performing options. These could be ranging on materials, ranging on manufacturing types, generating all of these options for us to then allow us to make the trade-offs as the engineer on cost versus performance. So for instance, we could have a casting solution with aluminum. This might be the lowest cost, but maybe the highest mass. We could have an additive manufacturing solution that's very high price, but also the highest performance. We could have a subtractive manufacturing solution that's somewhere in the middle. And then we could ultimately choose the one that we think fits the price and performance curve and requirements the most for our project. So one of the most famous examples of generative design that has been out in the industry is this one for General Motors. So General Motors took this seat bracket assembly that you see to the top left, traditionally manufactured as 8 unique components. They then generated a single outcome that could consolidate that assembly from 8 parts to 1, make something that's also lighter and stronger, but much more importantly than that, they were able to view 150 viable options to then start making trade-offs for. So when we look at generative design today, the process is actually very straightforward. So what generative design is going to do is it's going to take the entire volume that your part could fill, and it's either going to add or subtract material away from that to reach the final solve. So again, in the case of GM, this was able to provide them with a range of results that they could make trade-offs on. It could be material options, it could be manufacturing options. At the end of the day, this is allowing you to, again, make that cost versus performance trade-off. So when you're looking at any project you might have, the first thing that we have to do within generative design is we have to take our existing assembly and we have to break it down to what we call the preserved geometries, which are essentially the keep-ins, and then the obstacle geometries, which are the keep-outs. So we'll show that on an end-to-end workflow later, but that's really the only geometry considerations that we have to make. Now, a lot of people are familiar with those General Motors generative examples and some of these other ones you might see on the screen. And one of the major misconceptions that we've seen throughout the industry is that people think that generative design is only made for things like additive manufacturing, these very organic, unrestricted shapes. But as we look at the future of generative design and even some of the things that's happened recently, generative design is really expanding itself to reach more of the traditionally manufactured market. So what's changing within generative design that's making this applicable to much more than just additive? Well, the first is that when we launched generative design over a year and a half ago, the only constraint that we had was additive manufacturing at the time. So that's why a lot of the examples that you'll see throughout the industry only apply additive manufacturing. But we've worked very hard to make traditional manufacturing a viable output for generative design as well. So from there, we could get casting, we could get things like 3 and 5 axis CNC, 2.5 axis milling, and even things like 2 axis cutting. All of these are manufacturable outcomes that we can get from generative design today. And then next would be cost analysis. So when we're looking at generative design outputs, as an engineer, we need to know more than just the performance of these outcomes. We also need to know how much each one of these will cost. So we partnered with a company called A Priori Technologies. So now when we generate all these different options, we can also accurately look at how much the cost for each one will be. So before moving into the next section, I'd like to launch our second poll question of the day, and you should be seeing this come up now. The question is, which persona matches your role? Okay, thank you for everyone that answered that question. We will share the results. It looks like the majority of people say that they do everything, which is great. I mean, generative design has the ability to impact not just engineering and the design, but also the manufacturing areas of your company as well. So no matter where you fit as far as these personas, generative design can provide some value. So again, thank you for everyone that answered that question. So we talked a little bit about what's changing within generative design, and the primary reason that this is now applicable to the mass market is that generative design is no longer just exclusive to additive manufacturing. When we look at running a generative design project today, as we're setting up our manufacturing constraints, of course we can do the unrestricted, the additive, but we can also do things like milling, two-axis cutting, and then frame solving as well. So this provides you as an engineer, not just the ultra high performing additive solution, but it also provides you with the cost effective and more traditionally manufactured solutions at the same time as well. So from here, you can start to select to find the one that's the most appropriate for you. And in the end, in this case, we're taking what could essentially be a two-axis cut part that was still created with generative design, so it still has all of those advantages. So the next thing, so we have generative design for traditional manufacturing. We showed two-axis cutting, but also 2.5-axis CNC. So in this case, we were able to take what was a human-created part within number one. We were then able to generate a higher performing, traditionally manufactured outcome in option number two. And then we were able to take that and apply the human touch within number three. So again, generative design is not just for things like additive manufacturing. It can truly be applied to traditional manufacturing as well. So this second primary driver that's bringing generative design outside of just the world of additive manufacturing and into subtractive and traditional manufacturing is that we're bringing costing analysis to generative design as well. So again, we partnered with a company called A Priori Technologies. And now as we're running a generative design solve, we can take all of those additive results, all of the subtractive results, casting and everything else, and we can actually view the cost for each one. So here you can see this is a subtractive manufacturing part that we've highlighted in the top right. It has a price range and a median price. And this, again, is allowing the engineer to make the choice on the right trade-off to move forward with. So as we look at this today, and to close out the why around generative design, when we're talking about generative design, people immediately think about improving product performance, reducing mass, creating stronger, more compliant components. But that's only one small piece of this. For the vast majority of people, the things you should be looking at within generative design are actually reducing product cost and increasing productivity. And that's something that we've never been able to see within generative design before. So next, I'd like to talk a little bit about accessing generative design. And with that, I'd like to launch our third poll question of the day. So the question is, which potential advantage of generative design would apply you and your company the most value? Okay, we'll leave this open for a few more seconds. And thank you for everyone that answered that poll. So when we're talking about the potential advantages, it looks like improving product performance is something that's the most important for everyone out there. Increasing innovation capacity would be second. So exploring a wider range of options for your products. And then accelerating product development would be tied there as well on increasing innovation capacity. So once again, thank you for everyone that answered that question. Again, really what we're trying to make clear is that generative design is more than just an additive manufacturing tool. Okay, so next I'd like to spend a few minutes talking about how to access generative design. So we'll show an end-to-end workflow here in just a little bit. That starts off with your overall assembly with an inventor. We'll then take, in this case, a robotic end effector and the sub-assembly or the component that you like to run through generative design, and we'll bring that over to Fusion 360 to run through the generative design process. We'll then take that, we'll export the CAD, and we'll bring it right back into Inventor. So one of the main things that we want to talk about, if you have the product design and manufacturing collections, you actually have access to everything that we're showing today, and you might not be aware of it. Fusion 360 is a part of the collection, so this is something you could start doing. And the other very important part to this is that we're not trying to replace Inventor. So if you have your assemblies, your sub-assemblies, everything within Inventor, we're using generative design through Fusion as a piece of that workflow that we're adding in to provide generative design. So if you have access to the product design and manufacturing collections, there's really only two steps that you need to take to start running generative design today. First is to log into your Autodesk account and assign a user access to Fusion 360, which is again a part of PDMC. And then second would be to download from the Autodesk account, and you can start using Fusion and generative design and everything that we're showing today right away. So the last thing I should cover on this is when we're running a generative design solve, we leverage the cloud to give us those hundreds and thousands of outputs, and then ultimately loading back editable solid CAD geometry that's been created for us. So using the cloud, we have what's called cloud credits, which we'll talk a little bit about later on. But when you generate a study within Fusion 360, it costs 25 cloud credits. And to download the solid CAD geometry in the back end, it costs 100. So before moving on to the next section, I'd like to launch what could be the final poll question here of the day. We talked a lot about the manufacturing types within generative design, so additive, subtractive, injection molding, casting. Which one of these would be the most important for you coming out of generative design? So we'll wait just a few more seconds. And thank you for everyone that answered that question. So it looks like the majority of people are actually interested in additive. So this is, of course, a great use case of generative. While we talk about traditional manufacturing, you can always use it for additive as well. Second would be subtractive manufacturing, followed by frame structures, which we don't have quite yet, and then injection molding. So thank you for everyone that answered that question. So the next thing I'd like to talk about is how to actually set up the design space for generative design. So if we look at the swing arm of this motorcycle, it's a very complicated generative output. But when it comes to the setup point, it's actually very easy. So within generative design today, there's only two types of geometries that we need to create, extract, or take out of our existing assembly to run a generative design solve. Those are preserves and obstacles. So the first, when we look at our swing arm assembly, and this is our existing swing arm, the first thing we need to look at is our preserved geometries, which are the geometries that we know that need to be kept in within the final solve. So from here, we can break down the model looking at assembly features. So things like geometry that we know has to be kept in for mating, for fixtures, for a bolted location, anything that we know that we need to have within our final generative solve is what we'll actually create as the preserved geometry itself. So next, we also need to create our obstacle geometries. And this is really the opposite. With obstacle geometries, we're looking at creating or extracting geometry, telling generative that we can't generate anything within these sections. So it could be things like moving parts, it could be fastener and tool access, it could be the assembly itself. This is the geometry that we're telling Generative to avoid. So from here, we can quickly create the preserves and obstacles and we can start solving. So again, looking at this swing arm, we can quickly call out the preserved geometries and what those are. We can then create the obstacle geometries, again, telling Generative Design what to avoid. We start applying our loading conditions. We select our manufacturing types, and very quickly we can generate that entire range of options that we talked about. So from there, again, a very simple starting point is the geometry creation, the loading conditions, and using generative design, we can create geometries like you see on the screen that would be impossible really using any other technique. So next, I'd like to cover an end-to-end workflow. We'll start off with an Inventor, showing that subassembly or that assembly that I talked about, and how to use that within the context of Fusion and generative design to create a higher performing product. So again, when we look at the workflow for generative design today, right before this, we'll start off with that assembly with an Inventor, and we'll take out that subassembly that we'd like to improve. So in this case, it's a robotic end effector. So we'll take that gripper and we'll bring it over into Fusion 360 to start the generative design process. And this process always follows the same 4 pieces. The first is that we have to create the design space. The design space, again, are those preserves and those obstacle geometries telling generative design what to keep in and what to avoid. Next, we'll actually set up our generative design solve, looking at things like our loading conditions, our manufacturing types, and our materials. Third, we'll start to explore that range of options. So we provided generative with our requirements, our objectives, and now generative design is doing the work to produce all those outcomes for us. And as the engineer, we can start doing the cost versus performance trade-offs. And then finally, generative design creates solid editable CAD geometry for us. So we can quickly generate a editable CAD model that we can adjust, validate, and post-process. And from there, we can take that solid CAD model and send it right back to that original Inventor assembly. So as we take a look at this today, so starting off within our assembly with an Inventor, we will isolate just the gripper and just the robotic end effector components or the subassembly that we'd like to send over to Fusion 360. Now there's a couple different ways of sending the files over to Fusion. If this is something you'd like to learn more about, you can feel free to reach out to us anytime. What we're actually showing here is Fusion Team Associativity, where using the connector, we're actually able to select the files here and then send them over to our cloud files within Fusion 360 itself. So once we have that within Fusion, and I'll quickly bring up the product itself. For those that are not familiar with Fusion, I'll provide a quick overview. So Fusion is a CAD, CAM, simulation, and generative tool that's all connected in the cloud. So this allows us to do a couple things since it is in the cloud. It allows us to collaborate with team members a little bit easier, but probably the most important thing for us is that it allows us to leverage the power of cloud computing to do things like generative design. So if this was a subassembly that was brought forward, all that we would need to do is go to the generative workspace, and I'll show some of this pre-set up for you, but we need to start extracting all of the information for our preserves and our obstacle geometries. So first you can see we have our preserves here. Again, this is the gripping location of the object that the end effector actually needs to pick up. So that's geometry that we can quickly create either in Inventor or in Fusion. And we have the 2 fixed locations of where we know that the gripper needs to connect on the other side. Next, we have our obstacles. So we know that we can't generate anything into the object that we actually need to pick up. We know that on the inside of all of our preserves, we also need to have a bolted connection, so we can't generate anything into that section either. And using all of this information, we have the geometry set up that we need again very quickly. Next would be we'd start applying all of our loading cases. So moving from left to right, we've called out the preserve geometries, we've called out the obstacles. Next, we'll set up our load cases. So you can think about load cases as the conditions that our part will actually face within real life, right? So if it needs to grip at 500 pounds and it needs to lift a 200-pound part, this is where we're putting in all of those conditions for generative design to apply to. So on the left, you can see I have a series of load cases, load case 1, load case 2, and load case 3. We can apply as many of these load cases as we need to truly represent what's happening to this part in real life. So the first one, we could apply a gripping force. So we have, again, in this case, about 45 pounds applied to each one of these teeth. And then we have our robotic end effector constrained on the location towards the robot arm. So very quickly, we've applied our preserves and our obstacle geometries. We've applied our loading conditions, and next we're going to apply our objectives and our manufacturing and material types for the generative solve. So the first one for objectives, we have, this is actually what generative design is solving to. So we can choose to either minimize mass while keeping a certain factor of safety, or maximize the stiffness of the component while keeping a specific mass target. So in this case, we could say minimize the mass of my part while keeping a specific factor of safety of, let's say, 2 in this case. Next would be our manufacturing types. So within our manufacturing selections, this is where we're actually applying that entire range of manufacturing selection that we talked about before, right? So it's much more than just additive. It's also milling, casting, 2-axis cutting, and all of these can be applied within the same project at the same time. So the first message you'll see at the top asks for production volume. So this is actually what links to our costing analysis in the back end. So if we had to create 2,500 of these pieces, the per unit price is going to be very unique from if we had to just create 25. Next would be the unrestricted manufacturing. So unrestricted manufacturing means ignore all of the manufacturing considerations and just produce the perfect part. So this is sometimes very useful for the more unrestricted and less support-focused additive manufacturing technologies. So things like laser powder bed fusion, or things like multi-jet fusion from HP. These are all techniques that apply very well to the unrestricted manufacturing types. Next would be more conventional additive manufacturing settings here within additive. Within the additive settings, we can apply a maximum overhang angle and a minimum feature size, and it will automatically produce the self-supporting parts in the positive X, the positive Y, and the positive Z. Next, we have milling. So within milling, again, we can apply traditionally manufactured constraints to our parts. So here we can set up a series of configurations for things like 3-axis milling, 2.5-axis milling, and 5-axis milling to give us a range of options that we can start to compare against. Next would be 2-axis cutting. So this is if we're actually cutting this out of a plate using, let's say, water jet or a plasma cutter. Here we're specifying the cutting direction. And then with casting as well as the final selection, we're selecting the ejection orientation, a minimum draft angle, and then a minimum and maximum feature size. So this is actually the most important settings that you will place within any generative design. They actually allow the final parts you're producing to be manufacturable. So please keep aware of everything you're applying within those settings. And then finally, for our material selection. So the idea within generative design is that we don't want to just optimize for one material type and one manufacturing option. We really want to apply a wider range of options to then make more informed trade-offs. So currently within the solve, we have stainless steel, aluminum, titanium, and then another version of aluminum in 6061. So within generative design, we can put up to 7 materials at the same time, multiplied through all of those different manufacturing types to give us that range of outcomes that we talked about earlier. So here you can see in just a few steps in setting up the preserves and obstacles, the loading, the objectives, the manufacturing, the material types, we're able to get a generative setup very quickly. Now, the last thing that we could do before actually generating the solve in the cloud is we could run a local previewer. And what the local previewer is doing is it's looking at all of those constraints and load cases and making sure that everything will work once we actually launch this off in the cloud. So you can see a timeline has been created in the bottom right. And in just a second, you'll start to see a transparent geometry appear in the part. And really all that we're looking for in this is just to make sure that the geometry can connect in the preserves and that it's moving in the direction that we would expect. So after we've seen the successful preview like the one that we see here, we can stop the preview and we can go ahead and then actually generate this in the cloud. So I'll fast forward just a little bit here to actually look at some of the results. So what we're doing now is we're moving over to the Explore environment. Explore is where we take those hundreds or thousands of outputs and we actually start making those trade-offs that we talked about before. So again, we have a range of materials, a range of manufacturing types, and you can see all of these thumbnails appear on the screen representing a unique solution to that project that we set up. Some of these might actually be materials that are not strong enough that they've had to expand but actually couldn't reach the solving criteria. Some of these have their own unique manufacturing types, so that's why every single one of these is truly a unique and successful solution to the project that we set up. So on the filters to the left, we can quickly look at the manufacturing types themselves. So we can filter and look at only the unrestricted. Again, these are going to be the most organic, probably lightest, but hardest to produce components. Next, we have our more traditionally additive manufacturing constrained parts. So if we click down on one of these, you can see this is a part that's meant to be self-supporting in the positive Z orientation. So if our platform is here, everything is self-supporting vertically from that, from the overhang and from the minimum feature size that we set. Next would be our 2-axis cutting solutions. So 2-axis cutting, this is providing us with something that could be cut essentially out of a plate. So with this one, you can see that it made a series of pockets throughout that part, but again, it's providing us a very affordable generative design solution to work with. Next, we'll have our 2.5-axis CNC. So 2.5 is actually providing us something that could be machined within pockets in either 1 or 2 setups. So in this case, if we look at a 2.5-axis component, you could pretty easily machine this, again, providing you something that's higher performing, but also something that's traditionally manufacturable. Next, we have our 3- and 5-axis solutions. These are providing a little more organic CNC subtractive manufacturing options here. These could all be manufactured with subtractive manufacturing, but they're just going to be at a higher price point. And then finally, we have our casting solutions as well. So within casting, we're looking at a specific ejection orientation and then meeting a minimum feature size from that. So we looked at the manufacturing types. We also have a range of materials. So we have 6061, we have Tie 64. All of these are unique solutions to what we set up. Now, as you look to the top, there's a few other ways to really start to filter down and find the right solutions. We can look at a properties view for each one of these outcomes, saying what the material, the manufacturing type, and the properties of that specific outcome are. And we can also view these graphically. So we could say, let's compare cost versus mass. And now we're really making that trade-off that we've talked about this entire time on performance versus cost. So once you've found the generative outcome that you'd like to move forward with, again, we talked about how generative design is actually creating solid editable CAD geometry for us to take back. So all that you have to do is you click in the iteration or the outcome that you'd like. So let's say it's this very organic solution here. And you go to the export tab at the top and you create a new file from an outcome. So as we look at this component, again, very organic. This is an unrestricted manufacturing type, so something that could probably only be made with additive manufacturing. And as we click on the new file that's been created, in just a few seconds, a new window will appear within Fusion 360, showing us that new generative CAD geometry that was again created for us. So when we talked about improving productivity, and if you were trying to make an additive ready robotic end effector like the complexity that we see here, for me, it would take me at least weeks, I would think, but with generative design, we can set it up, compare all those different manufacturing types, and then actually get solid editable CAD geometry on the back end. So you can see the timeline in the bottom right. This will take just a few more seconds, and then we'll open up this part itself in a new window. So one thing I should mention, I do see at least one hand raised. Please feel free to type in questions as we are finishing up the presentation. We have about 15 more minutes for the presentation today. So please feel free to type in questions either in the chat window or the Q&A, and I'll try to either address those live or at the end of the session. So here you can see a new window appeared and we have that generative component. The first thing, just to really understand what Fusion is doing with these, is you'll see a timeline to the bottom left. And as we scale this back, you can see our preserves been created here first. So these are, again, what we told Generative we need as the keep-in geometries themselves. It then brings forward the obstacles, so everything we told Generative to avoid. It created T-spline geometry out of that very organic generative geometry that we created. It combined those together to then create just one final solid outcome part. So here in the dropdown, you can see all of this is contained as one solid editable CAD geometry. Now what this history allows us to do is it allows us to go in and make adjustments to this very complicated organic geometry quickly. So for example, if I click twice on our organic geometry to open it up, we could start coming in and we could thicken struts or close holes or make any adjustment that we think that we need to make. So in just a second, you'll see that this is now a T-splines model. And what we can do with this is we can come in and say, maybe we'd like to thicken this strut. So we can select one of these faces, select edit form, and we can automatically select that strut and then thicken that. So here I can do an automatic feature selection for the strut. And I can just click and drag this out. And thicken this strut to whatever we might need. So if we didn't have tools like T-splines and all of this organic modeling, to make adjustments like this to this generative geometry would take us a really long time. We'd probably have to create a series of planes, project and offset those, and then combine them together. But again, using these tools to automatically select features like struts and holes, and then to combine and smooth them out, allows us to make changes to again, these generative models very quickly. So once we're finished with this, we can select Finish Form. We'll drag this history to the right, recombining it as that one solid, and then we're ready to go. So the final thing that I talked to here is we took a generative part that we had applied loading conditions to, all of these different manufacturing constraints, and we actually made an adjustment to that part after we sent it out. So how do we know that this part is actually still within compliance? So what we can do within Fusion 360 is that once we've generated an outcome, we also have the simulation workspace to actually validate any of those changes very quickly. So here in just a second, I move the history again to the end, but we'll move over to the simulation environment and it will bring in all of those original load cases that we had. So as I click to the workspace drop down at the top, it will say, it looks like this model came from generative design. Do you want to use the setup information? And while I say yes, in just a second, it will show us all of the load cases, the material selection, and everything else. And all that we have to do within simulation is just press solve to make sure that we're validating any changes that we made to that model. So that's a quick walkthrough of setting up the generative design within Inventor, kicking it over to Fusion, running through the generative workflow within Fusion, sending out an output, and then validating. And just to quickly show you what some of these different manufacturable outcomes look like, this is the end of that robotic end effector itself. We can see we have the original component here. Next, we have an example of a 2-axis outcome just to really show you the range of solutions that we can produce. Again, this would probably be the most cost effective because we could really cut this out of plate. Next, we have our 2.5-axis manufactured solution. This would be our next most cost-effective solution. It's creating pockets that could be machined with probably just a single setup. Next, we have our additive manufacturing solutions. So these are meant to be something that could be self-supporting from a specific orientation. These are going to be a little bit higher performing than the CNC solutions, but probably a little more costly as well. We have our unrestricted. So one of these for an aluminum alloy, and then one that's a little bit organic, which is the one that we just looked at. So again, generative design can provide us all of these solutions across a range of extremely high performance, but also lower cost as well. So once we have our generative component, and this is showing actually the subtractive, the 2.5-axis subtractive component that we created, we can go back into our Inventor assembly and bring that right back. So again, the idea here with generative design and Fusion is not to replace what you do with an Inventor, it's to give you an added step to do something that you couldn't do before. So here within that Fusion team file, you could see all those different selections for those generative outcomes, and we can bring that right back into Inventor, remake those generative components within our assembly, and then very quickly, we've explored and created a higher performing outcome. So I'll fast forward just a little bit so you can see it here. And now we have our generative component within the assembly. So again, just to quickly close out, why generative is so important and increasingly important to the engineering world is that people have always thought about generative as a way to create models for additive manufacturing and improve product performance. And while that's certainly true, it's not the only way that you can apply generative. And for the mass market, it's going to be these first two that are the most important. And that's reducing product cost and increasing productivity. So with that, we have about 10 minutes left for Q&A. First, I'd like to apologize for the issues connecting at the beginning of the presentation, and I hope we were able to fill in some of that over the last 35 minutes. And I will remain on the line for as long as anyone has questions. So please feel free to either raise your hand or type them in the Q&A. So one question in the Q&A, this one from Mandel. Which software is more efficient and sophisticated for generative design, Inventor or Fusion 360? The answer to that would be Fusion, because Fusion is the tool that leverages cloud technology to do generative design. There isn't generative design technology within Inventor. There are some shape optimization technologies there, but it's very limited in the scope. So one of the ideas with Fusion having cloud technology is that we can bring files from Inventor and run them within generative design and really leverage the power of the cloud to do that. So thank you for the question. So a question from Brian, does the AM solution in GD automatically choose the orientation? What if I have requirements on the orientation of the part within the build chamber? So that's a very good question. In its current state, generative design will not automatically select an orientation for you. You will have to put the part aligned to either the X plus, Y plus, or Z plus orientation that you would expect for generative design. Obviously, this is a point of enhancement for us to come up with orientation selection as a part of generative design. It's just not something that's there quite yet. Another question from Brian, another great additive manufacturing question here. Will the AM solution only generate studies with 0 supports, or will it also generate a design with minimal supports? So the question to that is, with the unrestricted, you could call it additive solution, it will create you a solution that has that would require supports everywhere. So it's ignoring the supporting structure itself. The other side would be the traditional additive constraints, which will create only a self-supporting part. So you're completely right. We're missing something in the middle where there needs to be minimal supports, maybe an option for supports. And this goes along with your question of the supporting orientation. It's something that we're working on. And if you'd like to connect on that offline, we might be able to show you a little bit more about what we're doing. Question here as well, is there any FEA report for the build models? So within generative design today, when you set up the load cases and you get that final outcome, it is not carrying any of the information as an FEA report itself. What it is giving you is the setup that you can go into either Fusion simulation package or now our partnership with ANSYS to then revalidate and get a full FEA report from that model. Now, the reason that we do that is because when we generate these models and create a solid outcome, you would expect a slight variation in some of the connections between geometries and things like that. So it's always good to revalidate, again, either in Fusion simulation or in ANSYS, especially if you've made some change to that final generative outcome. Okay, we have a few more minutes. Once again, I will wait on the line as long as anyone has questions, so happy to answer those. Okay, looks like there are no new questions coming in. I will attach my email address in the chat window if anyone has any questions after this webinar today. Once again, apologies for the issues connecting at the beginning. But if you have any questions around generative design or where the technology is going, please feel free to send me an email at matt.lemay@autodesk.com. So once again, thank you for everyone that joined today, and I hope to work with many of you in the future.